Okay, so what had we seen so far? We had seen the circle packing theorem, implying that every planar graph can be represented as the intersection graph of interior disjoint disks, and we had seen that this readily implies the planar separator theorem. So this brings forth the following natural question. What other graph can be represented as intersection graphs? What kind of graphs have separators, small separators? And what can we do algorithmically with such graphs? And as Yogi Berra said, when you get to a fork in the road, take it. So I'm going to touch all 3 points. Of course, it turns out that Yogi Berra said it when he was minus 12 years old, which is a really young age for anybody to say anything. So, we're given a set of objects in the low dimensions, and we look on a ball, and the density of the ball is the number of objects that intersect this ball, and their diameter is bigger than the diameter of the ball. So this is the density of the ball, and the density of a set of objects is just the maximum density over all possible balls. So this definition was explored by people in computational geometry interested in coming up with a way to model realistic inputs, because a lot of algorithms have worst case behavior which is never observed for real world inputs, because real world inputs are much nicer than worst case input. In particular, we would expect all natural matches, most natural inputs to be low density, while of course there are inputs that are not low density, for example a large number of segments batched up together. Okay, so now that we have a set of objects that has low density, so what do I mean by a set of objects that have low density? I mean a set of objects such that their density is a constant, right? So we have a set of low density, and we can just naturally look on the intersection graph, and we will any graph that can be realized, the intersection graph of a set of low density objects in low dimensions, would be called a low density graph, right? So low density graphs have many interesting properties. The first is that you can overlay them together in a natural way, right? You take 2 sets of objects that have low density, you take their union, you overlay them together, you get an intersection graph of both sets of objects, and this new set of objects has low density, right? The density is the sum of the old density, but starting with constant, it's still a constant. Similarly, these low density graphs are degenerate in the sense that there is always a vertex that has constant degree. To this end, just look on the smallest diameter object in the set of objects. Clearly, it must intersect only a constant number of other objects. As such, the corresponding vertex has constant degree. Remove it and repeat. So this in particular implies that low density graphs have a linear number of edges, and are in fact has a constant chromatic number. Low density graphs are also separable. The proof I just showed you for the planar case just goes through verbatim in this case. And on the negative side, such graphs can have arbitrarily large clique minors, which is of course bad news, because having arbitrarily large clique minors implies that potentially they can have quite dense structures hidden in them. So to see that, let's consider this set of diamonds, that just the set of squares in vertical columns as seen on the slide. A row of dust, just disks in rows, and we take the overlay, we get this grid structure. And now if we identify all the objects in the column in the row, we take their union, then we get this L-shaped region. And if we do it for every row and column, we get those 5 geometric shapes where the intersection graph is a clique of size 5. Now, of course, if you look on the original set of objects, its density is a constant, and 5 here is completely arbitrary, right? So I can construct an arbitrarily large clique by, just building a bigger and bigger grid, which is very bad news, right? Because it says that low density graphs can hide inside themselves, this rather dense cliques. However, we are not doomed, and there is still redemption, and the redemption follows by carefully quantifying how quickly does the graph on the left, the original graph, deteriorate into a clique. And for this I need this definition of a T-cluster. So a T-cluster is a subgraph that has a center vertex, and all other vertices are T hops away from the center vertex. And now what I do, I take the original graph and I partition it into T-clusters, disjoint T-clusters, and we just take the intersection graph of those T-clusters. By that I mean every cluster gets a vertex, and I connect two vertices if and only if the two corresponding clusters, there is an edge connecting vertices that belongs to them. Okay, so in particular, a graph that can be generated by this process is called a T-shallow minor, right? So a T-shallow minor is just, you take your graph, you break it up into T-clusters, and you collapse the T-clusters into vertices, removing self-loops and parallel edges, etc. So a graph induces a large set, but finite nevertheless, of T-shallow minors, and the intuition is that as we increase the value of T, we can get a denser and denser graphs, right? So specifically, we are interested in looking in the growth of the worst case growth of such a graph. So we look on all possible T-shallow minors. We look on their the ratio between their number of edges and number of vertices. This is up to a factor of 2 the average degree in the graph. So we are essentially asking what is the T-shallow minor that have the highest average degree for the given graph, and we define this function to be f of t, right? So think about f of t as the worst average degree you can generate by collapsing T-clusters into vertices, and we're interested in how this growth function behaves. Okay, so to get a feeling for this somewhat bizarre definition, consider this graph, right? So this graph is the 8 by 8 by 2 clique, and we break it into clusters where every cluster is 2 vertices. So after we collapse those clusters, we get the graph on the right. The graph on the right has half the number of vertices, but the number of edges went down by slightly less, so this graph is a bit denser, right? And this is the graph where we collapse 3 vertices into a single cluster, and we get this. And now we collapse 4 vertices. Again, the number of vertices goes down, the number of edges goes down more slowly, so the graph becomes more dense. And this is the graph we get in this case for when we clump together 8 vertices. So we get this graph, which is in fact contains the bipartite clique K88 as a subgraph. Okay, so that's what the growth function captures. It captures how quickly the graph becomes denser. Okay, so let's see some concrete examples. So planar graphs, for example, are minor closed. So you collapse the cluster, you still end up with a planar graph. And as such, in particular, planar graphs have linear number of edges. So their average degree is a constant, and the growth is a constant. So f of t is always a constant for planar graphs. Not very interesting. On the other end of the scale, constant expanders, one can easily show that every T-shallow minor can have only 2 to the O of t vertices, and as such can have at most 2 to the O of t neighbors. So the growth is bounded by 2 to the O of t, exponential. And one can show that for low density graphs realized in constant dimension, the growth function is polynomial, right? It's t to the power of t roughly times the original density, which is polynomial. And in particular, this idea was has a more abstract class. So this abstract class is this polynomial expansion graph. Those are all the graphs that have growth, which is a polynomial functions. And in particular, low density graphs are polynomial expansion graphs. And this notion of polynomial expansion graph was defined by Nesetril and Osana de Mendes. And in particular, those people have a very nice book classifying various classes of sparse graphs and what can be done efficiently with them, and so on. And this book, opening this book is like opening the Pandora box, because you suddenly realize that there is a huge classes, there is a huge collection of different classes of graphs, and I'm listing on the slide some of them. I kind of listed them by inclusion, but very roughly, because the dependency between those classes is way more complicated than linear. You would have to see the book for more details. Okay, let me mention another interesting property of polynomial expansion graph, and as such also of low density graph, which is that in fact you don't need in these T clusters, you don't need them to be disjoint, right? So you can cover the graph with a large collection of T clusters, not necessarily disjoint. The only requirement is that no vertex participate in too many such clusters, and you take the intersection graph of those clusters, and this intersection graph has low density, right? So, or more, what do I mean by that? So if this is a low density graph, you end up, the intersection graph is also low density. If you start with a polynomial expansion graph, the intersection graph of the cluster is also polynomial expansion graph. So this is very interesting, because it means that, so by the way, before going any further, the right way to interpret this cluster, if I assign a cluster to every vertex, then the intersection graph can be interpreted as locally doing something like squaring the graph in a controlled fashion. Which of course in general you cannot do it for regular graph, even for a star, because if you square a star you get a click, right? So you really, even for a star, if you square it and you still want to get a sparse graph, you have to do it in a very controlled fashion. Okay, now the important thing about this property is that it implies that those classes of graph, both low density graphs and polynomial expansion graphs, are in fact very robust, right? You take those graphs, you torture them in any way you want, you add some edges, you locally square them, you delete some things, you insert some things, they still remain in the same family. This is this is very different than planar graphs. Planar graphs are very brittle. You do anything with planar graphs and they stop being planar. So this is kind of a very nice property. Okay, another interesting property of those graphs is that they are, if you have a polynomial expansion graph, a hereditary polynomial expansion graph, oops, let me try again. So a nice property of this graph is that if a graph has polynomial expansion, then it has a hereditary sublinear separator. By that I mean you take any subgraph, this subgraph is going to have a separator of size which is small compared to the size of the subgraph. And this is an if and only if, right? If you give me a graph such that for every induced subgraph there is a small separator, then this graph is a polynomial expansion graph. So you can think about polynomial expansion graph as just all the graphs that have an effective sublinear separator, which is algorithmically a very useful property. Okay, let me also quickly mention that there is a somewhat curious duality property to this graph. So if you give me a set of low density objects, I can compute a tiling of space by computing just, some quadri or a compressed quadri of space that agrees with the set of objects. And if I add the leaves of this quadri, the region that corresponds to the leaves of this quadri to the collection of objects, I end up with a set of low density objects that have slightly larger density, but now I have a behavior that looks very much like duality, right? There is a way to travel between original vertices in the graph using the underlying geometric space. So that property should be useful for something, but I don't know about any application for it. So it would be useful to use it effectively for something.